In this video, we will talk about the relationship between equilibrium and kinetics. We will also discuss how to determine the equilibrium constant given concentrations, as well as the relationship for the equilibrium constant given a balanced chemical equation. The term equilibrium should not be confused with equal. When an equilibrium is established, the rates of the forward and the reverse reactions are the same. However, that does not mean that the concentrations of the reactants and products are equal. It means that how fast the reaction is proceeding in the forward direction is equal to the rate that it's proceeding in the reverse direction. So some reactions reach equilibrium only after almost all of the reactant molecules are consumed. We say that those reactions, the position of the equilibrium, favors the products. Other reactions reach equilibrium only when a small percentage of the reactant molecules are consumed. We would say that those reactions favor the reactants, or we say that the position of equilibrium favors the reactants. Still, other processes have equilibriums in which neither the forward nor the reverse are favored, in which you have close to half of all the reactants are used up and converted into products. Previously, when we were looking at kinetics, what we were doing was looking at how the rates change with concentration over time. What we found is typically as the reaction proceeds, the rate of the forward direction slows down, and it depends on the order of your reaction to what extent it slows. Equilibrium occurs when the rate of the forward direction is equal to the rate of the reverse. So if we start out with most of our components in the form of A and B in our reactants, the rate of the forward direction is going to be much faster because the concentrations that we plug in to our forward rate law would have very high values for A and B. Conversely, the rate for our reverse reaction, our rate law is listed here for the reverse, would be slow because the values that we're plugging in for the concentrations of C and D are low. But as the reaction proceeds, the concentrations of A and B decrease as they are converted into our products. Because they are being converted into C and D, the values for C and D increase. There will be a point at which the concentration of A times the concentration of B times the rate constant for the forward reaction is equal to the value that we have for the rate constant of the reverse times the concentration of C and D. The equilibrium constant, we will be listing this as a capital K as opposed to our rate constants, which are lowercase k. So capital K, equilibrium constant, is actually equal to the ratio of the rate constant for our forward process divided by the rate constant for our reverse. If we take our equality up here and rearrange it, moving the A and B to the right and the K reverse to the left, we come across this equation here. K forward over K reverse is equal to the concentrations of C times D over A times B. Essentially, we take our product of our products, so our products multiplied together, raised to their respective coefficients, divided by our reactants, raised to their respective coefficients. The reason that we move all the constants to one location is it is convenient to have all of your constants lumped together. So our equilibrium constant is equal to the ratio of our rate constants, which itself is equal to the concentrations that we achieve when we are at equilibrium. We can do the same process for a mechanism that contains multiple steps, each step of which needs to be able to establish an equilibrium. So let's say that we are looking at our overall reaction of 2A plus 3B goes to C plus 4D. And let's say for argument that the proposed mechanism is 3 steps. The first step, part 1, is 1A plus 1B goes to E plus 2D. The E then we goes and participates in step 2. Step 2, note we need 2 E's for this to occur. This produces 1 F. That F gets used in the third step, reacting with a B. Now, at first look, it might appear that our 3 reactions do not sum up to our overall reaction. However, in step 1, it produces 1 E, and in step 2, it requires 2 E, which means that our step 1, the individual reaction that is listed for step 1, will actually need to occur twice, or twice as frequently as step 2. So essentially, when we're adding things together, we will need to take reaction 1 times 2 in order for us to have sufficient E to carry out reaction 2. So if we take our process here for step 1 and double everything, that would be 2A plus 2B goes to 2E plus 4D. That gets us our 2A, it gets us our 4D, and it gets us one of our 3 B's. The 2 E's produce an F. That F consumes another B. That would get us all the B's that we need. And it produces 1 C. So we end up with our overall balanced chemical equation. So if we're trying to show how this process can give us our equilibrium constant, what we would first need to do is write out our relationships for each step. So for step 1, the rate laws for the forward would be K1 times the concentration of A times the concentration of B. And if we say that this is establishing an equilibrium, then the rate of the forward process is equal to the rate of the reverse. So we're going to use the negative subscript for our K values to indicate that that is for the reverse process. So the positive values that we will have, the positive subscripts are going to refer to the forward reaction, and the negative values in the subscripts will refer to the reverse process. So the reverse would be K minus 1 times the concentration of E times the concentration of D squared, right? And that's the reason we're squaring the second one is because there's a 2 here for the D. Now, previously when we had been talking about rate constants, we had said that for elementary steps only, we can take the coefficients in front and use those as the exponents for that individual process. We are doing the same thing here. Our step 2 would be K2 times E squared is equal to K minus 2 times F raised to the first power. The last one is K3 times F times B is equal to K minus 3 times C. Now, if we're trying to come up with a way of re-expressing all of these, we need to keep in mind that one of the rules for our overall rate laws is that we can't have our intermediates listed in our equations. The same holds true for our equilibrium constant. So our intermediates are E, right? E is consumed, E is produced and then consumed, and so it is an intermediate. Same with F. F is produced and then consumed, so F is an intermediate. So we need to come up with a way of re-expressing E, and we need to come up with a new way of re-expressing F in terms of reactants. So let's start with E because it's part of reaction 1. So because we have an equilibrium established where the rate of the forward process is equal to the rate of the reverse, we can take our equation 1 and move everything that is not E to one side. This will give us the concentration of E is equal to what is on the left-hand side, K1 A B. And then to get E by itself, we had to divide both sides by K minus 1 times D squared. We can rewrite this as our concentration of E is equal to K, capital K1 times A times B over concentration of D squared. And for this, we're saying we're going to let K1 be equal to little k1 over little k minus 1. Okay, so we have a way of expressing E in terms of reactants and products. We need to be able to do the same thing with F. So we can take reaction number 2 and rearrange this. We can replace our value of E here with what we just came up with for a way of re-expressing E. So that would give us concentration of F is equal to little k2 over little k minus 2 times E squared. So that would be the entire thing that we just came up with. So that would be capital K1 times A times B over concentration of D squared. What's inside the set of parentheses is E, and because here we have E squared, we will square this. Okay, so if we distribute the 2 inside, that gives us capital K squared times K2 times K minus 2 times concentration of A squared B squared over concentration of D to the 4th power. We will also take our another equilibrium constant, capital K2, and we're going to set that equal to K2 over little k minus 2. Okay, we can now plug the value we determined for F, or the expression we have for F, into our third series of rate laws. This gives us K3 times this thing here. And for this, I'm going to replace our K, little k2 over k minus 2 with our equilibrium constant there. So that gets us times capital K1 squared times K2 times A squared B squared over D to the 4th power. Okay, so this whole part here is essentially our way of expressing concentration of F. So that would then be times our concentration of B. This is equal to K minus 3 times our concentration of C. Okay, I'm now going to move all of our constants to one side and all of our concentrations to the other. So I will divide both sides by K minus 3, essentially taking our K minus 3, moving it to this side, and then taking all of our concentrations, dividing both sides by that, which essentially will shift this to the other side. This will give us little k3 times capital K1 squared capital K2 over K minus 3 being equal to the concentration of C divided by concentration of A squared B to the 3rd, right? And the reason it is to the 3rd is because we were taking this B here times the B squared there, and that gets us B to the 3rd. That whole thing was being divided by the concentration of D to the 4th. Okay, we can do a little bit of cleanup. To do that, however, I'm going to need a little bit of space, so I will clear some of our work to the top. So rearranging this, we will also use an expression for an equilibrium constant for K3. K3 is equal to little k3 over capital K minus 3, which would give us capital K1 squared times K2 times K3 is equal. Now, our value down here in the denominator, we have the D in the denominator of the denominator, which means that it gets moved up to the numerator up top. That gives us concentration of C times concentration of D to the fourth power over the concentration of A squared times the concentration of B to the third power. Now, on the left-hand side, all of these K's are constant, so we can lump them all together into an overall K value. So we're going to call this capital K, and that will be equal to capital K1 squared, capital K2, capital K3. So what we have is that the ratio of our products raised to their respective powers over our reactants raised to their respective powers is equal to capital K. Note that the powers that they are being raised to, each one of these values corresponds to the coefficient in the balanced chemical equation. So the C has a 1, the D has a 4, the A is 2, and the B is 3. So what we will say is that for an equilibrium system, the capital K, the equilibrium constant, is equal to the products raised to their respective coefficients divided by our reactants raised to their respective coefficients. So this will work for any system in which all of your substeps in your mechanism are able to establish an equilibrium. If the overall process has this double arrow, that's what it's saying. This type of process is able to establish an equilibrium. In order to have an equilibrium, each one of your individual elementary reactions needs to itself be in equilibrium with its forward and reverse reactions. So the equilibrium constant can be determined from the balanced chemical equation. Taking a generic balanced chemical equation, A of A plus B of B goes to C of C plus D of D, the equilibrium constant will be equal to the concentration of the products raised to their respective coefficients, that quantity divided by the concentration of our reactants raised to their own coefficients, and those coefficients again come from the balanced chemical equation. So what we'll be able to do is, if we are given a balanced chemical equation, we'll be able to come up with the expression for the equilibrium constant. Similarly, if we are given the equilibrium constant expression, we would actually be able to derive from it what the balanced chemical equation must have been that gave rise to that equilibrium constant equation. Right? So if we were given this term or this equation down below, we could actually deduce from it what our balanced chemical equation must have been. Anything that is in the numerator is a product, anything that is in the denominator is a reactant, and then their respective powers are the coefficients that you would put in front of the balanced chemical equation. Now, as we had shown in the previous slide, we can actually derive our equilibrium constant from the rate constants for the elementary steps in a mechanism. Because the rate constants are temperature dependent, equilibrium constants that they make will also be temperature dependent. So equilibrium constants, just like the rate constants that they come from, are temperature dependent. They only change with temperature. So if we look at an example of hydrogen reacting with iodine, both as a gas, at 445 degrees Celsius. So each one of these setups is run at the exact same temperature. Our product is going to be hydroiodic acid, or HI. Now, what this table is essentially showing is a series of different reaction setups and trials. Each row represents one trial in which the initial concentrations and our final concentration vary between trials. The second set of columns, so column 4, 5, and 6, are what those concentrations eventually reach when the system establishes equilibrium. The last of our columns is the equilibrium constant. So if we take the values from the equilibrium concentrations, plug them in to our equilibrium constant expression, what value do we get out? So if we start with a system with everything in terms of reactants, no products, we will establish these values here for our equilibrium concentrations. What we will find is that at 445 degrees Celsius, the equilibrium constant using those respective equilibrium concentrations comes out to be 50. If instead we start with no reactants and only product, we will get different equilibrium concentrations, but when we plug that into our overall equilibrium constant equation, we get the exact same value of 50. If we start with equal concentrations of everything, we yet again get different values for our equilibrium concentrations, but when you plug those values into our equilibrium constant, you get the exact same 50 as our result. If you do twice as much hydrogen as iodine and no hydroiodic acid, you get different values for your equilibrium concentrations, but the ratio that we find in our equilibrium constant expression gives us 50 again. Similarly, if you do twice as much iodine as hydrogen with no hydroiodic acid, you get different concentrations for your equilibrium, but the ratio from your equilibrium constant gives the exact same value. So no matter how you start the process out, as long as you're doing it at the exact same temperature, you'll get the exact same value every single time, as long as you give it enough time to reach equilibrium.